Hello, welcome to the lecture 11 of 11 of game theory. Okay, I forgot to set the alarm clock. Okay. We have been talking about Nash equilibrium. What is the real meaning, implicit meaning behind the Nash equilibrium? And then it's like they have to promise, they have to point out the Nash equilibrium first, then everybody will keep the promise, kind of implicit meaning. Anyway, the basic concept is, you should not so confused about how people get into the Nash equilibrium. It is natural for you to, how come the Japanese drive on the left side? How come the Koreans drive on the right hand side? It's natural you got to wonder. However, the Nash didn't ask it. Okay, John Nash is a mathematician. All he said is, once they begin to play Nash equilibrium, nobody would change. Nash didn't care why all Koreans drive on the right-hand side of the road. Nash didn't ask. All Nash has said is, once every Koreans drive on the right-hand side of the road, nobody in Korea would dare to want to drive on the left-hand side. Okay, because there would be a lot bigger probability to get an accident and you got killed, kind of thing. Okay? What is the great thing about Nash equilibrium? Just one thing. You can find out Nash equilibrium almost every game, especially when there is a finite players, when there is a finite strategies, then it's guaranteed. Nash proved that it's guaranteed that game has a Nash equilibrium. So for the first time, we have a concept, equilibrium concept, which can point out a equilibrium means prediction of every game, almost every game. Okay? Why did I say almost? Because if the strategies are infinite, there is a possibility Nash equilibrium may not exist. However, if it's infinite and finite, less than infinite, then always exists. Okay, so that the fact that the Nash equilibrium always exists overcome any kind of shortcomings of the property of Nash equilibrium, like multiple Nash equilibria and things like that. So look at this. This game must have Nash equilibrium. Have you tried this game? Like somebody is holding a coin or something in the hand. It can be an odd number of coin or an even number of coin. Tom is holding it in his hand. Of course, Tom knows whether it's an odd number and even number. On the other hand, the opponent Bill, other player, do not know it, whether it's odd or even. When I was a kid, I played this game a lot. So when Tom hold odd number of coins and Bill call odd, then Bill is correct. So Bill gets 10 cents, Tom lose 10 cents. This kind of game. On the other hand, when Tom hold odd number of coins, but Bill said even, then this time Bill was wrong, not incorrect. So Bill has to pay Tom 10 cents, negative 10. That's why Bill has, and Tom gets 10 cents. Okay, this is the game. Let's check. This game must have Nash equilibrium. If odd and odd, can this be equilibrium? No. Tom would change to even so that his payoff would become negative 10 to 10. Okay, then what about even and odd? 10 and negative 10. This time, Bill changed from odd to even, then his payoff would become from negative 10 to 10. If Tom changed from even to odd, then his payoff would increase. That's why even cannot be an Nash equilibrium. What about the last candidate? Odd and even. Tom would get 10, Bill would get negative 10. Bill would change to 10 by calling odd. So none of these four are Nash equilibrium. So, oh my God, John Nash got Nobel Prize because he proved every game has a Nash equilibrium, but then we found out this game doesn't. Is it correct? Actually, you are correct and Nash is correct too, because there's a pure strategy Nash equilibrium. Okay, I'll verbally explain. There are two kinds of strategies: mixed strategies and pure strategies. Until now, we just learned pure strategy. If some cars driving on the left-hand side, they keep driving on the left-hand side. Okay? And we just checked. If Tom hold odd, he always hold odd. And Bill always called odd. But if you play this game, Tom actually randomized become odd and even, because let's assume that Tom always hold even. It's known to everybody. What would Bill do? Call even all the time. So Tom is gonna lose all the time. So when Tom choose one strategy, one pure strategy with probability 1, Tom will definitely lose. That's why Tom randomized between odd and even, so that Bill cannot be sure whether Tom holds odd number of coin or even number of coin. This kind of randomizing is being called by game theorists as mixed strategy Nash equilibrium. The most well-known, and we have looked at, rock, scissors, paper game. I wonder how many of you play rock, scissors, paper game and just play rock all the time. Probably not. You would mix between rock, scissors, paper. Because you mix the three of them, we call it randomize, because I hope you're not gonna mix rock, then scissors, paper, rock, then scissors, paper. If you do that, Bill is going to win. Whenever you do rock, he'll do paper, scissors, rock, paper. So when you do rock, scissors, paper, Bill is going to do paper, rock, scissors. Then Tom is going to lose all the time. So the word randomize means Tom mixed these three, but shouldn't have any rules, like rock, rock, paper, scissors, 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 paper, rock, something like that, so that Bill would never guess what is going to be next. Okay? Likewise, Bill should mix too. So in this rock, scissors, paper game, there is no pure strategy like the odd number, even number game. However, it has a mixed strategy Nash equilibrium, which we are going to have a look. So when John Nash says, like, most of the game, almost every game has a Nash equilibrium, especially when there's a finite number of strategies, he meant not only the pure strategy equilibrium, but as well as the mixed strategy equilibrium. I'm a little bit worried that how motivated you are by watching this, taking this lecture, because if you haven't noticed that the game theory is quite mathematical, by now I hope you do, because this is very, you have to understand the mathematical logic, tables and things like graphs and things like that, in order to understand the real game. So bear with me. And like this medical fund depletion kind of game, I'm going to lead you after this explanation and calculations, especially this mixed strategy Nash equilibrium has many calculations. Then you will realize that it's useful. So we have to, I'm going to teach you how to find out the mixed strategy Nash equilibrium. In order to do that, you have to follow the next logic. Number one, Nash has the famous Nobel Prize winner Nash proved that rock, scissors, paper game has a Nash equilibrium. Definitely. Why? There are two players, three strategies each finite and finite, so got to have a Nash equilibrium. And if you have a look, none of these are pure strategy Nash. Rock, 0, 0. Tom will choose from rock to paper, so that from 0 to 1 improve. What about scissor and rock? The Tom will change from scissor to rock, then it improve from -1, 0, scissor to paper, -1 to 1. When you kind of prove that scissor and rock cannot be a Nash equilibrium, you don't have to think about always like scissor to paper. Scissor to rock improve from -1, 0 is good enough to prove that scissor and rock is not a Nash equilibrium. So if you check these 9 things, the candidates of pure strategy Nash equilibrium, none of them are Nash equilibrium. So we regard the Swedish Nobel Prize committee is very smart people. If we accept that, then this rock, scissors, paper game must have the mixed strategy equilibrium because John Nash said so, and he got Nobel Prize. The pure strategies that are played with a positive probability in the mixed Nash equilibrium should have the same expected payoff. Wow, what is that? Okay, let's go to the next page. Let's assume that you are playing a rock, scissors, paper game against a machine. It's not a human being. You go to Las Vegas, there is a machine which plays rock, scissors, paper with you. But then it's well known, and it's not a lie at all. It is, the government guarantees that it gives rock with 50% of time, scissors 30% of time, paper 20% of time. Okay, so you can trust this. So half of the time, the machine gives you rock, 30% of time, the machine gives you scissors, and only 20% time, the machine gives you paper. What will you do? Two most frequent answers are, you will, some students already say, I will choose rock with 30%. Why 30%? Because scissor is 30, rock wins over scissor, so 30%. Scissor wins over paper, but paper would be given only 20%, so scissor 20% of time. Paper, the rock was given 50% time, paper wins over rock, so 50%. So the higher winning probability, the higher probability you will give. That's one answer, possibility. There are some other students who says, I'll never give rock, never give scissor, I'll only give paper. Why? The machine gives rock most frequently, so I'm going to concentrate myself to gain against rock. So if the machine gives you scissor and paper, okay, I was wrong. But 50% of time, I would be right. Which answer would be clever? We would calculate. Okay? Relax your mind because it is involved with a lot of calculation. Let's go. let's assume that what is the probability of always playing paper? Your opponent gives you rock with 0.5 probability, 50% of time. When you are keep playing paper, if your opponent, the machine, gives you rock, you are gonna win and get 1. And we are calculating the expected payoff. If the machine gives you seizure, the probability is 0.3, because you are giving paper all the time, you will lose and give -1, get -1. So if you keep playing paper with 50% time, you will win, 30% time you will lose, and 20% time it will be a tie and you will get 0. If you add up, your expected payoff by playing paper all the time would be 0.2. I'm sorry. This is 0.2. What am I doing? So this red number here, I'm sorry, 0.2, because 0.5 minus 0.3. I'm so dumb. Okay, so you are smarter than your professor. Congratulations. So 0.2. Now go back here. I hope I didn't make any mistake here, but let's see. So here, rock, scissors, paper would be played with 30, 20, 50% of time, like the first strategy. Then, with 0.3 probability, your opponent will give you what? Give you seizure. Oh, no. You are giving rock with 0.3, 30% of time. Sorry. You are giving rock 30% times, seizure 20% time, paper 50% of time. Now, the first one is your expected payoff from rock. The second thing is your expected payoff from seizure. The third line is your expected payoff from paper. Okay? And we already calculated the expected payoff from paper would be 0.2. I'm sorry, once again, 0.2. But then you play paper with 0.5 probability, so 2 multiply 0.5 would be 0.1. That's why we have 0.1. The first line, what is the probability, expected probability by playing rock? 0.5 is a tie because the other guy gives you a rock. 0.3, the other guy gives you seizure, so you win 1. 0.2, the other guy gives you paper, you lose -1. So total 0.1. Multiply 0.3, the probability that you play rock, 0.03 would be the expected payoff. You give seizure with probability of 20%, that's why 0.2. And if you play seizure, you lose to rock and get -1 with a 50% chance, because the machine gives you rock 50% chance. You are gonna be tie, 0.3, 30% of time, because the machine gives seizure 30% of time. You are gonna win and get 1. When the machine gives you paper, the probability that the machine gives you paper is 20% of time. So in total, it's going to be -0.3 multiply 0.2 is -0.06. So in total, it's going to be 0.07. And if you keep playing paper, I'm sorry, once again, 0.2. So which is bigger, 0.2 or 0.07? 0.2. So if you were confused which is bigger, if you play the first strategy, your average payoff would be 0.07. On the other hand, if you play the second one, it's 0.2. Huge difference, almost three times bigger. So you play this. Okay, I know this calculation might scare you, but look at this. This is multiplying and adding up. It's like elementary school arithmetics. So if you just calm yourself down and check one by one, remembering the probability and payoff multiplied would be the expected payoff. But then you multiply one more time because rock's expected payoff, you play rock 30% time, 0.3. Caesar's expected payoff, multiply 0.2 because you play Caesar 20% time. Paper's expected payoff, multiply 0.5 because you play paper 50% time. On the other hand, if you play paper, all these with 0.2, because you play only paper only, it's 100%. That's why 0.2 stays. Sorry, 0.2. So you will choose to play paper all the time. It's same thing. I mean, paper is best, and then the rock is second best, and Caesar is worst. How can you maximize it? You just randomize between the best one, second best one, third best one? No. You just keep choosing the best one. Then you would be the winner. That beats every other probability. So paper is the best strategy when the machine plays rock so often. So then keep playing paper. Okay? So the lesson is, if one pure strategy is better than the other, people never choose the second best, third best strategy. They will all in to the best strategy. Okay? What does that mean? This means this. Now you should understand. When you play rock, scissors, paper in real life, okay, think it over. You keep playing, you never play scissor and paper in your life, just keep playing rock because man is rock. No. Whether you're a man or lady, you randomize between rock, scissors, paper. You do not choose one of them. You probably chose all three of them in your life. But then, as we have seen this game against machine, if scissor is best among the three, you're not gonna mix. You will just keep playing scissor. If paper is better, you'll keep playing paper. But then, the fact you are mixing them means they are equally best. Otherwise, mixing them doesn't make sense because you can maximize your payoff and profit by what? By choosing the best strategy only. But then in rock, scissors, paper, you are randomizing between rock, scissors, paper. That can only make sense when rock, scissors, paper give you the same payoff. Okay, this is recorded lecture, so if you confused, didn't hear, rewind it, hear it more. So once again, John Nash says, every game has Nash equilibrium, including the mixed thread Nash. The rock, scissors, paper should have won according to John Nash, but does not have the pure strategy Nash equilibrium where people choose one strategy. And in fact, people are randomizing between rock, scissors, paper. But then, when rock is better than scissors and paper, you are supposed to keep playing rock, never scissors and paper. As I explained by this rock, scissors, paper machine case. In that example, keep playing paper all the time gives you the best payoff. But then, throughout our life, we randomize between rock, scissors, paper, which automatically means rock, scissors, paper gives you the same payoff. We are going to use that fact to find out the mixed strategy Nash equilibrium of rock, scissors, paper game. The beeping sound is on, so we have to do that in the next class. So this is end of lecture 11, and you're about to enter lecture 12 in the next lecture. See you soon.